Hi, today I'm going to present you our latest work from CVPR. When designing a general-purpose visual system, it's helpful to have a wide field of view for a variety of tasks, such as maintaining context awareness and detection of environmental hazards. However, it's also helpful to be able to perceive fine details for tasks such as threading a needle or reading text. Having both abilities is desirable. However, with present computational paradigms, having both abilities is challenging, and the reason is that images that integrate a wide field of view and high resolution are often computationally heavy to process. Downscaling an image solves the issue of computational needs, but loses critical details. This is an open problem in computer vision, and at the time of making this video, leading AI models struggle to process images larger than the limits below without downscaling. However, for humans, processing a wide field of view and fine details is not a problem, because humans employ an information reduction strategy called foveation. Foveation essentially decreases our visual acuity outside the center of our visual field. A natural question arises, which is, can machines adopt this mechanism, and is it useful? In this study, we compare the performance of vision language models on two subsampling schemes. On the left, inspired by the human visual system, and on the right, inspired by image downscaling. With interpolation, we're able to use existing architectures and compare their performance on the two sampling schemes given the same amount of information in both. In visual question answering, our findings reveal that variable sampling performs better than uniform sampling, regardless of fixation point location, as indicated by the standard deviation bars on top of every chart in the middle. Additionally, we demonstrate that variable sampling outperforms uniform sampling in most question categories, and even outperforms full resolution images in certain cases. This is an interesting example showing a question that can be answered with the details preserved under the variable sampling scheme. Secondly, our findings reveal that higher resolution brings diminishing returns. Variable sampling appears to perform better than uniform sampling beyond just 3% sampling density. And last but not least, 3% of pixels are enough to achieve 80% of baseline performance, which is a remarkable finding given that visual question answering is a complex task and often requires information that can be in very low resolution areas. So, a natural question arises, which is, why does variable sampling perform better? In CNNs, we discover key differences between models trained with uniform sampling and models trained with variable sampling. In models trained with variable sampling, we discover filters that range from a spectrum of full resolution and a spectrum of uniform resolution. We demonstrate that these filters develop specialization or selectivity similar to how the human brain's neurons have selectivity. In vision transformers, we measure a metric called the attention distance. The attention distance effectively measures how far away do image patches attend on average. Here's an empirical example showing that tokens taken from the red points attend more globally in models trained with variable resolution. This is also confirmed by the quantitative metric attention distance, measured across several layers of the vision transformer. The key takeaways from our study are that 80% of performance is achievable with just 3% of pixels, even on complex visual tasks. Secondly, models trained with variable sampling exhibit human-like representations, namely neuronal selectivity and a globally acting self-attention. Future vision language models can benefit from a human-inspired vision approach with multiple fixations, and they don't need higher resolution images, because those by themselves bring diminishing returns. Future vision language models can be made more efficient by employing a strategy similar to the human visual system. Thank you.